Heat and mass transfer. Heat in thermodynamics, heat is in joules. In heat and mass transfer, heat is in joules per second, rate of heat transfer. In thermodynamics, PV path energy conservation, heat loss by steel is equal to heat gain by water. MSCPS 90 minus TF is equal to MWCPW TF minus 30. TF is equal to equilibrium temperature. Here steel block 1 kg at 90 degrees, 10 kg of water at 30 degrees. Example, we'll reach TF thermodynamics. Ambient water absorbs heat only from steel block, not from any other source. Zeroth law of thermodynamics about thermal equilibrium. First law of thermodynamics, energy conservation. Second law of thermodynamics, heat always flow from high temperature region to low temperature region. Crash state. The main difference between thermodynamic analysis and heat transfer analysis of a problem is that in thermodynamics, we deal with systems in equilibrium. That is, to bring a system from one thermodynamic state to another thermodynamic state, how much heat is required is main criteria in thermodynamic analysis. But in heat transfer analysis, we evaluate at what rate this change of state occur by calculating rate of heat transfer in joules per second or watt. Modes of heat transfer: conduction, convection, radiation. Conduction, let us consider a metal rod is placed in a source of heat. Conduction is molecular lattice vibration energy transfer 30%. 70% of conduction is due to free electron transfer. Silver K is equal to 410 watt per meter Kelvin. Copper K is equal to 385 watt per meter Kelvin. Only K aluminium 200 watt per meter Kelvin. Steel K is equal to 17 to 45 watt per meter Kelvin. Metals molecular lattice vibration energy transfer 30% for metals only. Free electron transfer 70%. Flame free electron transfer. uh, Free electron transfer inside like this. Molecular lattice vibration is 30%. K pure metal greater than K its alloys. K iron greater than K steel. K copper greater than K brass. Brass is an alloy of copper and zinc. Definition: conduction is mode of heat transfer which generally occurs in solid due to temperature difference associated with molecular lattice vibrational energy and by free electron transfer. The reason behind all electrically good conductors are also generally good conductors of heat is their presence of abundant free electrons. Example: all metals, copper, silver. Notable exception of above statement is diamond, where K diamond is 2300 watt per meter Kelvin due to its perfect crystalline lattice arrangements. Non-metals: crystalline, amorphous. Crystalline, orderly and closely arrangement of molecules. Example: diamond, quartz, graphite. Amorphous, voids, gaps. Example: glass. K glass is equal to 1.5 watt per meter Kelvin. Thermal conductivity K. It is thermophysical property of material which tells about the ability of material to allow the heat energy to get conducted through material more rapidly. Note: insulators have very low thermal conductivity. Thereby can prevent heat transfer rate. Asbestos asbestos is equal to 0.2 watt per meter Kelvin used for roofs. Glass wool is equal to 0.075 watt per meter Kelvin. Refractory brick brick is equal to 0.9 watt per meter Kelvin used in furnaces. Polymethane foam (PEF) foam is equal to 0.02 watt per meter Kelvin used in refrigeration valves. Gases also can conduct heat as shown below. Kinetic theory of gases: C bar directly proportional to root 2. C bar is equal to root mean square velocity of a gas molecule. Air 1 mm high temperature plate, low temperature plate, high velocity, high temperature, heat conduction, low velocity, low temperature molecule. Gases conduct heat by molecular momentum transfer. When high velocity, high temperature molecules collides with low velocity, low temperature molecules, but in general, gases are very bad conductors of heat. Ki air is equal to 0.02 watt per meter Kelvin. Molecular momentum transfer during collision. As temperature of gases increase, their thermal conductivity also increases because at higher temperature gas greater molecular activity may result in more number of collisions per unit time and hence more momentum transfer rate. As temperature of gas increases, thermal conductivity increases, specific heat gap CP increases, kinematic viscosity increases, density decreases. Thermal conductivity, temperature, air, helium, H2. As temperature is increasing, K is also increasing. Liquid are better conductors of heat than gases. K watt is equal to 0.63 watt per meter Kelvin. Among liquids, mercury has highest thermal conductivity. KHg is equal to 8.43 watt per meter Kelvin liquid metal. Convection. A fluid with T infinity with speed of V infinity, TW hot plate, TW greater than T infinity, hot plate like heat will flow like this. Convection is a mode of heat transfer which generally occurs between a solid substance and surrounding fluid due to temperature difference associated with microscopic bulk motion of fluid transporting thermal energy. In case of forced convection heat transfer, this motion of fluid is provided by external agency like a fan or pump, whereas free convection heat transfer, the motion of fluid occurs naturally due to buoyancy forces arising due to changes of fluid because of its temperature change. Because of its temperature change. Radiation. All bodies at all temperatures emit thermal radiation except the body at 0 Kelvin, minus 273 degrees centigrade and minus 273.15 degrees centigrade. Radiation is a mode of heat transfer which does not require any material medium for its propagation, hence occurs by electromagnetic wave propagation traveling with speed of light. Electromagnetic waves, higher temperature plate, more emission, low temperature plate, lesser emission, vacuum chamber. Example, sun of 5800 Kelvin, electromagnetic waves, earth 0.1 micrometer, visible light 0.3 to 0.7, 100 micrometer, thermal radiation 0.3 to 100 micrometer, visible light. Okay, lambda micrometer. Electromagnetic waves spectrum. Note in any practical situation, all three modes of heat transfer may simultaneously prevail. But radiation mode of heat transfer completely predominates over conduction and convection, particularly when the temperature difference is sufficiently large. Example, mode of heat transfer between hot flue gases and refractory brick walls is large. In a large pulverized fuel-fired power boiler is predominantly by thermal radiation. Reason large delta T. Practical examples: sun, solar radiation absorber plate, solar plate collector. Sun, solar radiation, convection to outside air, convection to inside air, inside AC room, outer wall of the house, conduction in between. Ambient at 1 degree centigrade, convection 37 degree, Q conduction directly proportional to T1 minus T2, Q convection directly proportional to TW minus T infinity, Q radiation directly proportional to T1 power 4 minus T2 power 4. We have to substitute in Kelvin into sigma. Governing laws of heat transfer. Fourier's law of conduction, it states that rate of heat transfer by conduction along a given direction is directly proportional to temperature gradient along that direction and is also directly proportional to areas of heat transfer lying perpendicular to the direction of heat transfer. Qx is equal to minus dt by dx. Negative sign shows that heat is always flow in the direction of decreasing temperature, that is, it satisfies Clausius statement of second law. Q directly proportional to A. Qx is equal to minus Ka dt by dx. Dt by dx is slope. Minus K thermophysical property of material of slab. Qx. Newton's law of cooling. The law states that the rate of heat transfer by convection between solid body and surrounding fluid is directly proportional to temperature difference between them, and is directly proportional to area of contact or area of exposure between them. Q convection directly proportional to Tw minus T infinity, directly proportional to A. Q convection is equal to HA delta T. H convective heat transfer coefficient or film heat transfer coefficient watt per meter square. Fluid at T infinity, convective convection, hot plate TW. Unlike thermal conductivity, H is not thermal property of material, but it depends upon some of the thermophysical properties of fluid like density rho, the dynamic viscosity mu, specific heat capacity Cp, thermal conductivity K. Forced heat transfer coefficient, convection heat transfer, H is a function of V bar comma D comma rho comma mu comma Cp comma K. Rho mu Cp K are thermophysical properties. V bar is equal to velocity of fluid meter per second. D is equal to dimension of body. Use it to calculate a dimensionless number. In natural convection heat transfer, H is function of G beta delta T L mu rho C P K. Mu rho C P K are thermophysical properties of fluid, where G is equal to acceleration due to gravity, beta is equal to isobaric volume expansion coefficient of fluid, delta T is equal to Tw minus T infinity, L is equal to characteristic dimension of body. Water transfer the heat 25 times rapid than air. Ranges of heat H. Free convection in gases and vapors H is equal to 3 to 25 watt per meter square Kelvin. Forced convection in gases air only H is equal to 25 to 400 watt per meter square. Free convection in liquids water only H is equal to 250 to 600 watt per meter square Kelvin. Forced convection in liquids water only H is equal to 600 to 4000 watt per meter square Kelvin. Condensation heat transfer vapor to liquid H is equal to 3000 to 25,000 watt per meter square Kelvin. Boiling heat transfer liquid to vapor H is equal to 5000 to 50,000 watt per meter square Kelvin. Stephen Boltzmann law of radiation. The law states that radiation energy emitted from a surface of black body per unit time and per unit area is directly proportional to 4 power of absolute temperature of the black body. EB is directly proportional to T power 4 T in Kelvin. EB is equal to sigma T power 4 watt per meter square. Sigma is equal to Stephen Boltzmann constant. Sigma is equal to 5.67 into 10 power minus 8 watt per meter square Kelvin power 4. Black body is the body which absorbs all thermal radiation incident or falling upon the body. Black body, perfect absorber, ideal emitter, diffusive in nature. A thermal black body absorbing all the heat, all the incident thermal radiation may not appear black in color to human eye. Example, ice and snow. Conduction heat transfer integration of Fourier's law. Integration of Fourier's law. Case 1, conduction heat transfer to slab. Assume steady state heat transfer conditions, temperature not function of time, temperature not function of time. T1 or T2 Qx plus dx B x is equal to 0, x is equal to b. One dimensional heat conduction T is equal to f of x at x equal to 0, T is equal to T1 at x equal to b, T is equal to T2. Constant value of K, Qx is equal to minus Ka dt by dx watt. Integral x is equal to 0 to b is equal to integral T1 to T2 minus Ka dt. To satisfy steady state heat transfer condition Q not equal to f of x, Qx is equal to Qx plus dx. Qx is equal to Ka T1 minus T2 by B watt per meter square. Electrical analogy of heat transfer. Electrical thermal I ampere Q watt. EMF for delta V, delta T degrees centigrade or Kelvin. R it is a resistance ohm, R thermal. I flows R electrical delta V delta T Q. Ohm's law R electrical is equal to delta V by I. R thermal is equal to delta T by Q. For slab RTH is equal to T1 minus T2 by Q is equal to B by K Kelvin per watt. Higher the thickness of slab and lesser its thermal conductivity, more the thermal resistance offered by slab, and hence heat transfer rate will be lesser. Case 2 conduction heat transfer to composite slab. Assumption one dimensional steady state conduction heat transfer in two composite slabs. Thermal circuit T1, T2, T3, B1 by K1A, B2 by K2A, K1, K2, B1, B2. In case of slabs, area of conduction of heat transfer will not change in direction of flow. Rate of heat transfer to composite slab Q is equal to T1 minus T3 by B1 by K1A plus B2 by K2A. Heat flux Q by is equal to T1 minus T3 by B1 by K1 plus B2 by K2 watt per meter square. To find T2, Q is equal to T1 minus T2 by B1 by K1A is equal T2 is equal to degrees centigrade. Q is equal to T2 minus T3 by B2 by K2A. K2 is equal to degree centigrade. K1 less than K2. Q is equal to minus Ka by Ka dt by dx. dt by dx more, K lesser. Since dt by dx in 1 greater than dt by dx in 2 by slope K1 less than K2. Okay, one question, a plane wall K is equal to 1.15, inner surface at 1100, outer surface at 350 degrees. Then design thickness of wall to maintain steady state heat 2005, which is nothing but a Q by A. He gave Q by A 2500. K also given. T1, T2 are given. B have to find B. B is equal to 0.345. One more question. Here composite wall is used. Two both of thickness L. One is one conductivity with K, other with 2K. Left face of wall is at 600 Kelvin and that of right face is at 300 Kelvin. T1 is equal to 600 Kelvin, T3 is equal to K is 300 Kelvin, K1 is equal to K, K2 is equal to K. First draw diagram K to K. Here slope is more, here slope is less. Q should be same in both. 600 minus Ti by L by K is equal to 6 Ti minus 300 by L by 2K. Ti is equal to 400. You can draw the circuit also like this. Q must be same. Another question, low thickness sandwiched between two steel slabs. So, okay, two steel slabs. So, heat flux 10 kilowatt per meter square is supplied on one of steel walls, steel slabs. Boundary temperatures of slabs and assume thermal conductivity. Okay, considering one-dimensional heat conduction for configuration, thermal conductivity of material. Can QY is equal to 10 into 10 cube watt per meter square. QY is equal to 10,000 is equal to 500 minus 350 by 1 by K. We have to find K. It's easy. Here also just draw the circuit. And one more question. Just asked about interface temperature. Everything is given. Again heat draw circuit. Q is same. We will get T2. Then it is nothing but interface temperature. Again same model. Here just K1, K2 ratios are given. You can cancel it and we can again find TA. One more question. Here just given that T interface is T1 plus T2 by 2. We can use that and we can cancel top 2. Then we can get K1 is equal to K2. Convection thermal resistance, the RTH is equal to delta T by Q Kelvin per watt. RTH convection is equal to TW minus T infinity by Q. RTH convection is equal to 1 by HA convection K per watt. Here A convection means the area which is in contact with that fluid. Q is equal to HA TW minus T infinity. Conduction, convection, heat transfer through a composite slab. Assumption steady state one dimensional conduction, convection, heat through composite slabs. Q is equal to rate of heat transfer between hot gases and ambient fluid. Q is equal to Tg minus T infinity by 1 by H1A plus B1 by K1A plus B2 by K2A plus 1 by H2A watt. H1, H2, hot gases at Tg, Q, T2, K1, K2, B2, B1, B2, T3, colder temperature, Q is equal to Tg minus T infinity by 1 by H1A plus B1 by K1A plus B2 by K2A plus 1 by H2A. Heat flux is equal to heat transfer rate per unit area. Q by A is equal to Tg minus T infinity by 1 by H1 plus B1 by K1 plus B2 by K2 plus 1 by H2. Overall heat transfer coefficient, defining overall heat transfer coefficient to U as parameter which take into account all modes of heat transfer into single entity. That is from equation Q is equal to UA delta T watt is equal to UA Tg minus T infinity watt. Comparing 1 and 2, 1 by U is equal to 1 by H1 plus B1 by K1 plus B2 by K2 plus 1 by H2. If U value is more, the total thermal resistance in the entire circuit is lesser, and thus heat transfer rate will be higher. Here similar to above questions, but one side heat H is given, T infinity is given. So Q by A is equal to T1 minus T2, T1 minus this T infinity by 1 by H, 1 by H plus 1 by K, L by K. Similarly, here both sides H is given. We can draw the circuit. Q by A heat flux is equal to, we can get it. One more question with K1, K2. Here also same, draw the circuit. T interface was asked. Equate Q. Then we can get it. Here overall heat transfer coefficient is used. 1 by A is equal to L by A plus 1 by H1 plus 1 by H2. Radial conduction heat transfer through a hollow cylinder. T1 greater than T2, Q, R1, R2. T is equal to F of R, at R is equal to R1, T is equal to T1, at R is equal to R2, T is equal to T2, T1 greater than T2. Since temperature gradients are existing along radial direction, heat must conduct radially outwards from inner cylindrical surface at T1 to outer cylindrical surface T2. Unlike in a case of heat conduction through slab, here the area of conduction changes in direction of heat flow. At any radius r, area of conduction heat transfer is A is equal to 2 pi r L. Fourier law of conduction, rate of radial conduction heat transfer, Q is equal to minus Ka dt by dr. Q is equal to minus K 2 pi rl dt by dr. Q dr by r is equal to 2 pi kl d minus 2 pi kl dt. Steady state one dimensional radial conduction, integral r1 to r2, q dr by r is equal to integral t1 to t2 minus 2 pi kl dt. Q into ln of r2 by r1 is equal to 2 pi kl t1 minus t2. Q is equal to 2 pi kl into t1 minus t2 by ln of r2 by r1. Q not equal to f of r. To satisfy steady state condition, qr is equal to qr plus dr. The corresponding thermal resistance for radial conduction through hollow cylinder is R conduction is equal to ln R2 by R1 by 2 pi KL. R conduction is equal to ln R2 by R1 by 2 pi KL T1 T2. If thickness of cylinder is very small, that is R1 approaches to R2, and if conductivity of cylinder is very high, a very thin copper cylinder, the above conduction thermal resistance almost becomes zero, because K is high and R1 R2 almost equal, so 0. Radial conduction heat transfer through a composite cylinder. Assume okay here K1, K2, R1, R2, R3, T1, T2, T3, T1 greater than T2 greater than T3. Assume one-dimensional steady-state radial conduction heat transfer between innermost cylindrical surface at T1 to outermost cylindrical surface at T3. At R is equal to R1, T is equal to T1. At R is equal to R2, T is equal to T2. And rate of radial heat transfer through composite cylinder T1, T2, T3 ln R2 by R1 by 2 pi K1L ln R3 by R2 by 2 pi K2L. Q is equal to T1 minus T3 by this R1 resistance 1 plus resistance 2. With numericals, this is the question. It's in numericals, this is the question. Okay, innermost heat transfer per unit length. Radial convection conduction heat transfer in a composite cylinder. H1 is equal to inside convective heat transfer, H2 is equal to outside convective heat transfer coefficient. Just to draw the circuit, everything is normal. And inside 1 by H1 2 pi R1L, outside resistance 1 by H2 2 pi R3L. And this both are same as before. Assume steady state one dimensional radial conduction convection heat transfer between hot gases flowing inside an ambient colder fluid. Rate of heat transfer between hot gases and ambient fluid is Q is equal to Tg minus T infinity by sum of resistance. Defining overall heat transfer coefficient Ui, that is based on inside heat convection heat transfer area, and overall heat transfer coefficient Uo, that is based on outside outside convection heat transfer area, from the equation. Q is equal to Ui Ai delta T is equal to Uo Ao delta T. That is Q is equal to Ui 2 pi R1L Tg minus T infinity is equal to Uo 2 pi R3L Tg minus T infinity watt. Comparing 1 and 2, we get 1 by Ui is equal to 1 by H1 plus R1 by K1 ln R2 by R1 plus R2 by K2 ln R3 by K2. Okay. But in heat exchanger analysis, whether LMTD or effectiveness into method, U can be calculated 1 by U is equal to 1 by H1 plus 1 by H2 without fouling. Okay. Critical radius of insulation for a sufficiently thin wire H2, H1 hot fluid, sufficiently thin wires neglecting conduction thermal resistance. For sufficiently thin wires, putting the insulation around wire may result in increase of heat transfer rate instead of decreasing it. Consider a solid wire of radius Ra inside which heat is being generated by passing electric power. Let an insulation having thermal conductivity K is being wrapped around the given wire into up to radius RO. KH. The heat generated in the wire due to passage of current is radially conducted through the insulation from surface of wire, and then from surface of insulation heat is connected to ambient fluid at T infinity with the convective heat transfer coefficient of H. Let the Ti is equal to surface temperature of wire under steady state condition. Drawing thermal circuit for radial heat transfer between wire and ambient thermal circuit. T1 conduction ln RO by Ri by 2 pi K1 1 by H 2 pi ROL. The rate of radial heat transfer between wire and ambient. Q is equal to Ti minus T infinity by ln of Rho by Ri by 2 pi KL plus 1 by H 2 pi ROL. Treating all other parameters, that is Ri, L, K and H as constant. Now Q is equal to F of Rho only. For maximum heat transfer rate, dQ by dRO is equal to 0. D by dRO of this whole heat is equal to 0. RO is equal to K insolation by H. Critical radius of insolation. Physical significance of critical radius of insolation. QRO, it increases and then decreases. Maximum at RO is equal to K by H Q max. For sufficiently thin wires whose radius is less than critical radius of insulation, putting insulation around the wire will increase Q. In increase of Q, decrease thus is because of initially, which is more and more insulation is being wrapped around, there is rapid decrease in convection thermal resistance as compared to little increase in thermal conduction thermal resistance. The overall effect being decrease in thermal resistance and increase in heat transfer. This continues up to critical radius, beyond which any insulation added shall decrease the heat transfer rate. In case if the radius of wire is initially considered is already more than critical radius of insulation, any insulation wrapped around it shall directly decrease heat transfer rate. Application: electric power transmission cables. Insulation is put up around the electric power transmission cable to increase heat transfer rate between cable and ambient so that the temperature of cable can be maintained low, thereby its thermal resistance can be maintained low, thus transmitting more electric power. More insulation, T cable increases, R increases. Spherical electronic semiconductor devices. R critical sphere is equal to 2K by H. Insulation Q more Q generation. Critical radius is equal to K insulation by H is equal to 0.08 by 10. Here you should not bother about this K. Only insulation K we should consider. Increase heat loss to maximum and then decrease in heat loss as we increase insulation. It will be at some point and then decrease. Okay. R critical is equal to K insulation by H. Same here again, it is at this point. That is same. R critical, then electric current carrying capacity of the wire. Heat transfer increases, T cable decreases, R electrical decreases, more power can be transmitted. Okay, this thing is okay. Then sphere R critical is equal to 2K by H. R critical is equal to 2K by H. As thickness of insulation around a heated cable gradually increases from 0, heat transfer from conductor first increases and then decreases provided radius of cable initially taken less than critical radius. Radial conduction heat transfer through a halo sphere. This is sphere. T1 greater than T2, T is equal to F of R, at R is equal to R1, T is equal to T1, at R is equal to R2, T is equal to T2. Since temperature gradients are existing along radial direction, heat must conduct radially outward from inner spherical surface T1 to outer spherical surface at T2. Like in case of cylindrical heat transfer, here also area of conduction heat transfer changes in direction of heat flow at any radius R. Area of conduction heat transfer A is equal to 4 pi R square. Q is equal to minus Ka dt by dr, rate of radial heat transfer. Q is equal to minus K 4 pi R square dt by dr. Integral R1 to R2 Q dr by R square is equal to integral T1 to T2 minus of K 4 pi dt. Assume steady state one-dimensional heat transfer T not equal to F of time, Q not equal to F of R to satisfy equation of steady state. QR is equal to QR plus DR. Rate Q into minus 1 by R1 to R2 is equal to 4 pi K into T1 minus T2. Rate of heat transfer Q is equal to 4 pi K into T1 minus T2 into R1 R2 by R2 minus R1 watt. The corresponding thermal resistance is RTH is equal to delta T by Q. RTH conduction halosphere is equal to T1 minus T2 by Q is equal to R2 minus R1 by 4 pi K R1 R2 Kelvin per watt. Slab RTH is equal to B by K. Cylinder RTH is equal to ln R2 by R1 by 2 pi K1L. RTH sphere is equal to R2 minus R1 by 4 pi K R1 R2. The temperature profile here it is linear, here it is logarithmic, here it is parabolic. Okay. Composite sphere similar to cylinder, we can write it as R2 minus R1 by 4 pi K1 R1 R2, R3 minus R2 by 4 pi K2 R3 minus R2. Q we can write normal on. Generalized heat conduction equation. 3D steady or unsteady with or without heat generation. Q dot watt per meter cube uniform heat generation rate slab throughout the slab. Qx plus dx. Heat can be generated inside a solid body either by supplying electric power or by exothermic chemical reaction or thermonuclear fission. Consider a small differential element of slab of length dx as shown in figure. Let Qx is equal to heat conducted into element along x direction is equal to minus Ka dt by dx watt. Qx plus dx is equal to heat conducted out of element along x direction Qx plus dou by dou x of Qx dx watt. Heat generated within element is equal to Q dot into volume of element is equal to Q dot into ADX. Writing energy balance for x direction conduction through the element Qx plus Qgen is equal to Qx plus dx plus rate of change of internal energy with respect to time. Qx plus Q dot A dx is equal to Qx plus dou by dou x of Qx dx plus dou by dot of m dot c mcp d8 mcp tq dot a dx is equal to dou by dou x of minus ka dt by dx of dx minus dou by dot of rho a dx cp dt adx cancel everywhere, then k dou square t by dou x square plus q dot is equal to rho cp dou t by dou time t. Tau means time here. Consider writing energy balance similarly for all three directional conductions occurring along x, y, z direction simultaneously. We get k dou square t by dou x square plus k dou square t by dou y square plus k dou square t by dou z square plus q dot is equal to rho cp dou t by dou tau. Dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus q dot by k is equal to rho cp by k of dou t by dou tau. Rate of heating or cooling in Kelvin per second. Thermal diffusivity alpha, a thermophysical property of material as ratio of thermal conductivity of material and its thermal capacity. Alpha is equal to K by rho Cp. K watt per meter Kelvin, rho kg per meter cube, Cp joule per kg Kelvin, alpha meter square per second. Rho Cp is equal to heat capacity or heat storage ability. Alpha of a medium or material tells about ability of a material to allow the heat energy to get diffused through the material more rapidly. Higher conductivity of material and lesser its heat capacity or heat storage ability, more the value of thermal diffusivity. Alpha gases greater than alpha liquids, alpha air greater than alpha water, K less than K water, OCP air less than OCP water. Substituting the value of alpha dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus q dot by k is equal to 1 by alpha dou t by dou tau. If conditions are steady, t not equal to function of time dou t by dou tau is equal to 0, and if there is no heat generation, q dot is equal to 0. Dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square is equal to 0. Delta square t is equal to 0. Laplace equation in t. In case of one-dimensional heat conduction in a medium with constant properties, T is temperature at position x at time t, then dt by dt is proportional to dou square t by dou x square is equal to 1 by alpha dou t by dou tau. Dou t by dou tau is equal to alpha dou square t by dou x square. Alpha is equal to constant. Dou t by dou tau is equal to is directly proportional to dou square t by dou x square. Okay, dou T by dou tau or temperature profile is given, so dou square T by dou x square we can write it at x equal to dou T by dou T is equal to, we can find it. Heat generation in slab. Objective to get temperature distribution within slab T is equal to f of x. Assumption steady state heat transfer condition T not equal to f of time. Uniform heat generation, convection to fluid at T infinity, symmetric parabola T naught to 2L TW, x equal to minus L, x equal to plus L, x equal to 0, T naught. To maintain the steady state conditions of slab while generating heat, all the heat generated in slab must be converted to fluid either from one side of slab or from both sides. One-dimensional heat conduction, that is T is equal to f of x only. Uniform heat generation Q dot is equal to 0 and constant K. Dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus Q dot by K is equal to 0 is equal to dou T by dou tau. As it is steady and one-dimensional, these three are 0. T is equal to f of x dou square T by dou x square plus Q dot by K is equal to 0. Dou square T by dou x square is equal to minus Q dot by K. Integrating with respect to x, dou T by dou x is equal to minus Q dot by K x plus C1. Again integrating, T is equal to minus Q dot by K x square by 2 plus C1x plus C2. C1 and C2 are constants of integration that are to be determined from boundary conditions. One special boundary condition is x is equal to plus L and x is equal to minus L, T is equal to TW. That is, both sides of slab are subjected to same temperature. Note, the above can be possible only if both sides of slab are exposed to same fluid with same temperature and connect to heat transfer coefficient H. To satisfy this boundary condition, C1 is equal to 0. In case of both sides of slab are at different temperature, the C need not be 0. The temperature of slab is maximum when dt by dx is equal to 0. Minus q dot x by k plus C1 is equal to 0, and that is x equal to 0. We see maximum temperature at midplane of slab. We do not see maximum temperature at the midplane. In case if both sides of plane are at different temperature, let the maximum temperature of slab to be at x equal to 0, t is equal to t naught, c2 is equal to t naught. The temperature distribution within slab is T is equal to minus Q dot by K x square by 2 plus T naught. T naught minus T is equal to minus is equal to Q dot x square by 2K. Parabolic temperature distribution. At x equal to plus L or minus L, T is equal to TW. T naught to T is T max, T naught minus TW is equal to Q dot L square by 2K. T naught minus T by T naught minus TW is equal to x by L whole square. Non-dimensional format of temperature distribution. TW can be obtained from energy balance equation from steady state condition of slab. That is, heat generated in slab is equal to heat convected from the fluid. Q dot La is equal to 2H A into TW minus T infinity. TW is equal to Q dot L by H plus T infinity. T naught is equal to TW plus Q dot L square by 2K is equal to Q dot L square by 2K plus Q dot L by H plus T infinity. Case 2, the other case is one side of slab is perfectly insulated. Heat conducted at the insulated surface is equal to 0 minus Ka dt by dx is equal to 0. dt by dx is equal to 0. T is maximum at the insulated surface. Is T max parabolic Q conduction is Q conduction total is equal to total heat generated. 1D plate, one temperatures again 160 degrees, 120 degrees, K is given, and Q dot is also given. So d square T by dx square is given, Q dot by K is equal to 0. Then integrate C1, C2 get from 120 and 160. You can get a C1, C2 maximum at dt by dx is equal to 0. You can get x at T max also you can get. Okay, slab 3D object. 5 faces are insulated, 6 faces PQRS. PQRS, which is not insulated, interacts with ambient H. Okay, 10 watt per meter square. The ambient temperature is 30 degrees centigrade. Heat is uniformly generated inside the object at rate of 100 watt per meter cube, assuming the phase of PQRS to be uniform temperature. Its steady state temperature is Q dot into volume of slab. Q dot into volume of slab. For steady state conditions of slab, heat generated in slab is equal to heat convected from PQRS to fluid. Q dot into volume of slab is equal to HA PQRS into T PQRS minus T fluid. Okay. Consider 1D steady state heat conducting along x-axis to plane wall to the boundary surfaces x is equal to 0, 0 degrees to 100 degrees. Heat is generated to the wall must be greater than 100 degrees. The maximum temperature. Okay, it will be like this. Insulated uniformly insulated side there will be T max. dt by dx here is 0. Heat generation in cylinder. Q dot is equal to I square R by pi R square L. Objective to get watt per meter cube. Objective to get temperature distribution within the rod T is equal, that is T is equal to F of R. Assumption steady state heat transfer. T temperature is not function of time. To maintain the steady state heat transfer condition while generating heat, all heat generated in rod must be convected to fluid at T infinity surrounding the rod with convective heat transfer coefficient of H watt per meter square Kelvin. One dimensional radial heat conduction, that is T is equal to F of R only. Uniform heat generation and constant K. The generalized heat conduction equation in cylindrical coordinate system is given by dou square T by dou R square plus 1 by R dou T by dou R plus 1 by R square dou square T by dou pi square plus dou square T by dou Z square plus Q dot by K is equal to 1 by alpha dou T by dou tau. This is 0. R is equal to radial coordinate, Z is equal to axial coordinate, pi is equal to azimuthal coordinate. Dou square T by dou R square plus 1 by R dou T by dou R is equal to minus Q by K. R dou square T by dou R plus dou T by dou R is equal to minus Q dot R by K. D by dr of R dt by dr is equal to minus q dot r by k, integrating on both sides. R dt by dr is equal to minus q dot r square by 2k plus c1 dt by dr, again integrating, send r to this side. Then t is equal to minus q dot r square by 4k plus c1 log r plus c2. C1 and C2 are constant of that integration are obtained from boundary conditions. At R is equal to capital R, that is at a particular periphery or surface, T is equal to TW. At steady state conditions of rod, heat generated in rod is equal to heat conducted radially at surface is equal to heat convected from surface. Fourier's law. Q dot into 2 pi R square L is equal to minus k 2 pi rl dt by dr at r is equal to capital R. So dt by dr at r is equal to minus q dot r by 2k. Q dot r by 2k, here only pi r square will be there. C1 is equal to, comparing 1 and 2, C1 is equal to 0 as log r will not be, should not be there. C1 can also be said to be 0 because logarithmic function becomes infinity when r is equal to 0, that is axis of rod, but the temperature at axis cannot be infinity. The temperature of rod is maximum when dt by dr is equal to 0 minus q dot r by 2k plus c1 by r is equal to 0, r is equal to 0 at axis. Therefore, we see maximum temperature at axis of rod. Let the maximum temperature of rod to be T naught at R is equal to 0, T is equal to G naught, C2 is equal to T naught. T naught is equal to Q minus Q dot R by 4K plus C1 log R plus C2. This is 0, this is 0. The temperature distribution within rod is T is equal to minus Q dot R square by 4K plus T naught. T minus T naught is equal to minus Q dot R square by 4K. Parabolic temperature distribution at small r is equal to capital R, T is equal to TW surface temperature. T minus TW is equal to minus Q dot capital R square by 4K. T minus T naught by T minus TW is equal to small r by capital R whole square. TW, T infinity, T naught. The surface temperature Tw can be obtained from energy balance equation for steady state conditions of the rod. Heat generated in rod is equal to heat convected to periphery. Q dot into pi capital R square L is equal to H into 2 pi capital R L into Tw minus T infinity. Tw is equal to Q dot R by 2H plus T infinity. T max for T naught is equal to Q dot R by 4K plus Q dot R by 2H plus 2 infinity plus T infinity. If q dot values are very high and if h values are low, then the value then T naught values enormously increase, which may finally result in melting of wire, and this melting begins at axis of rod. It is generated, okay. T minus T naught is equal to q dot r square by 4k.